Hello everyone. As I promised, I am making the recordings. I thought that it is better to start from the beginning. Maybe some of you have misunderstanding parts from the beginning. So if you think that you know the last topics, the previous topics, you can skip them. Let's start. Okay, we discussed that when two or more processes cooperate with each other, the order of execution should be preserved. Why? Because if you don't do it, and it means that they are using the same resource, maybe some conflicts in the execution or some unexpected results can be produced. What is a cooperative process? Actually, we can simply say that if a process is waiting result to take that result and use for its need, or just the opposite, one process should produce something and the other one is waiting for that. So, or we can say, if one process is affect execution of other process or affected by another process. So this kind of processes are called cooperative process. And the generic name of which we are trying to make them, this kind of cooperative processes, in order without any problem, is called process synchronization. Here, as you see, we have a file, we have a shared memory, and think the beginning, the first process should write something here, and then this one should read. So the order of execution is something like that. If this one not write anything, there is nothing to read from there. So order of execution is very important in process synchronization. And we have several synchronization mechanisms for that to supply process synchronization. We will see most of them. For example, mutexes, semaphores, file logs. What happens if we don't we don't be ensure about the synchronization? Race condition may occur. What is raised condition? For example, if two or more processes are trying to access concurrently to the same resource, race condition will occur. And in this case, we may have it unexpected results or some conflicts. For example, here you can see that we have two processes. One of them is just making incrementation. The other one is making decrementation. If both of them are at the same time access to the same resource count, um, so this one tries to increment, this one tries to decrement. Maybe this count will be 6, 5, 6, 5, something like that. So it will not be the result that both processes are expecting. Okay, I'm not going to show you the videos that I put, I mean, this one to watch. You can watch if you want to have some more information. Okay, the critical section is a region that more than one program are trying to access. So we are called it as critical section. So to avoid the race condition among the processes, we need to assure that only one process at a time can execute within the critical section. Here, it is a good example, toilet example. When you are in the toilet, a public toilet, if you lock the door, no one else can by accidentally enter. But if you forget to lock, someone without knocking the door may enter. So it is a kind of race condition because you are using the toilet and someone else is trying to access to use the toilet. So to avoid this, we have to just apply some mechanisms. And the place that the memory part or whatever you called it, that part that more than one process need to access, we called it as critical section. And we can say, in other words, it is a part of a program which tries to access shared resources. Okay, so in a program, there is a part that it is trying to access shared resources while it is executing. This part is called as critical section. The resource that in the critical section is trying to access there can be a memory location, a data structure inside CPU, can be a location or any input-output device. Doesn't matter. So the critical section cannot be executed by more than one process at the same time. So only one process should be in critical section, because when more than one process is entering there, there's a risk of having unexpected results because they may change that memory element or something like that. So we will have some unexpected results. And operating system generally faces with the difficulties to solve this problem. That's why we said critical section problem. And it is designed some protocols to ensure that the race condition will never arise there. So only one process, to ensure that only one process can use at the same time the critical section. As you see here, all processes are inside the critical section. It is a scenario that we don't want that. So to synchronize the cooperative processes, the main task is to solve the critical section problem. So in this chapter, actually, we will see some algorithms that solving this problem, and we will analyze them. But to solve the this critical section problem, and also just supply the or ensure the synchronization between the processes, we should apply apply some criteria, and they should be successful, like mutual exclusion, progress, bounded weighting, and architectural neutrality. The first one, and we can say that the most important one, is mutual exclusion. What is mutual exclusion? Actually, to make it ensure that only one process are using the critical section at the same time. For example, here we can see that only process P is using the critical section. Then process P, while it is not using the critical section at that time, process A is using. And it is going like that. So this is called mutual exclusion. Only one process using this shared object. I mean, they are using, both of them are using, but in one time period, one of them is using, then another one is using. At the same time, they are not using. So by mutual exclusion, we mean that if one process is executing inside critical section, then the other process must not enter the critical section. So this is mutual exclusion. So only one process should use critical section. Of course, the others can enter later, but one at a time. The other one is progress. It means that if one process does not need to execute no need to enter to critical section. So it should not just stop other processes to just use the critical section. Okay, during the execution of a number of processes at the same time, it might happen that the order of execution of the statements in the critical section affects the final state of the values in the critical section. And we've seen that it gives a race condition, occurs race condition, and at the end may give some inconsistencies in the code. And these problems can be solved by applying mutual exclusion. But here, there may be a chance of starvation of other processes. What is starvation of other processes? Processes are waiting so long for another one. And when the starvation is just extends to infinity, it leads to a deadlock, which is a problem that all the processes are waiting for each other, and the problem cannot be handled at that time. So mutual exclusion alone cannot guarantee the simultaneous execution of processes without any problems. And also second condition known as progress. This one is required to ensure no deadlock occurs during such execution. So, if no process is executing in its critical section, and some processes wish to enter their critical sections, then only those processes that are not executing in their remainder section can participate in deciding which will enter its critical section next. So that means if some processes, think about that. What is a critical section? It is a part of the code that each program has to just have access to a memory location which some other processes have to access. So if one of them is accessing, the others should not be accessed. And sometimes while the processes want to access the critical section, more than one process, they should be just decide which of them will enter the critical section next. And also, the processes which they are executing in remainder section, what does it mean? They actually just quit from the critical section or something like that. So in this case, they don't just have right to decide about this thing. And this selection, the decision cannot be postponed indefinitely. So they should decide which one will access next. Okay, let me to give you an example related to progress. Suppose in the clothes section of a departmental store, a boy and a girl, boy A, girl B, want to use a changing room. Here, both of them wants to enter to changing room. And boy A just said, okay, I want to go first. And girl B should wait until boy A comes out. And as you see, the changing room is vacant. It means it is available. But boy A, okay, he decided to use the changing room first, but he didn't decide yet how many clothes he will take inside. So actually, yes, he's going to use it, but at the same time, he didn't finish execution of something else. In this case, girl B was ready to use it. Boy A actually it is not ready to use, but he is actually make the room occupied, but he didn't start to use it. So in this case, actually boy A is blocks the changing room, and girl B cannot enter the changing room because boy A is blocked it. So this kind of problems may happen, and progress is aiming to actually progress is not, but one of the mechanisms that should be applied is to ensuring the progress, we can say in other words, to not to have this kind of problems in the system. So in other words, boy A prevents girl B from using the changing room, even though he doesn't need to use it. So this is what the concept of progress was made to prevent. So if we continue to progress, we discussed that, but let me to again tell, the only processes that can participate in the decision making as to who can enter the critical section, this part. And critical section, actually, there is no need to be same statements of like that for different processes. Actually, we are using the same resource in critical section. Think about, we have two processes. One of them is using a variable for calculating a formula value, and the other one is using a variable just to make incrementation, something like that. So their aim in critical section may not be same, but they are using, they are trying to use the same memory part. So while they are aiming to use that critical section. And think about that like the toilet, like the changing room example. More than one process wants to use the same resource. There should be a decision making, and decision making should be between laws that are about to enter the critical section. Okay, so if a process is here or are executing some code before entering the critical section, or it is just close to enter the critical section, but before it should execute some code. But if any processes that are in remainder section, which is the section succeeding the critical section, they don't have right to just make decision about this process. The main job of progress is to ensure one process is executing in the critical section at any point in time, so that some work is always being done by the processor. This decision cannot be postponed indefinitely. In other words, it should take a limited amount of time to select which process should be allowed to enter the critical section. So while one process is executing and the others are waiting outside, they should decide which one will enter the critical section. So if it is not taken in a finite time, it leads to a deadlock, which simply we can say, for example, some process is waiting for to take some information, to give some information to the other process, and the others are waiting for the similar things. It is a kind of deadlock like this. This is just a symbolization of deadlock. Of course, we don't say that every time it is like that. And also maybe more than two processes may have a deadlock. It is just a symbolization. As you see, process one is waiting some resource, something from resource R1 to just put some result to resource R2, and process 2 is waiting some resource, some product from resource 2, and after make some calculation, it will put it to resource 1. So both of them are waiting to each other in this case, and it is a deadlock. Okay, the secondary one is of requirements, secondary part of requirements. One of them is bounded waiting. So we should be able to predict the waiting time for every process to get into the critical section. So a process must not be endlessly waiting for getting into the critical section. So we have to make a limitation. This is important as well. And the last one is architectural neutrality, which when we just think about that, we created a mechanism to solve of all these problems, or ensuring that it can be successfully done. We have to be sure that it is working for all architectures. It means If our solution is working fine on one architecture, then it should also run on the other ones as well. So this is architectural neutrality. We have to also think about that. So we find that solution, but if one architecture is not supplying that command or something like that, in this case, we can't say that it is architecturally neutral. Okay, we can just stop here. I will continue to record.